Previously, we observed how increasing the temperature increases the rate of reaction. This was achieved because the average kinetic energy, this amount of particles only possess the required energy threshold to initiate a reaction. In other words, enough energy to overcome the activation energy barrier, which is not many particles. However, by increasing the temperature increases this average kinetic energy, which means there's a greater proportion of particles to overcome the activation energy for a chemical reaction to occur. There's more particles with enough energy to break those bonds so new ones can be formed. We also looked at how increasing concentration of one or more reactants increases the rate of reaction, as long as they are in the same phase, as in gas or liquid. When concentration increased, more particles are packed into a given volume, so there's a greater chance the particles will collide more often. If we observe the reaction between potassium hydrogen tartrate solution and hydrogen peroxide, the potassium hydrogen tartrate decomposes, so these are produced, but it's the production of carbon dioxide gas that we can possibly observe. Mind you, this is super slow, so it's unlikely you actually see that. What a shame. Although, when we increase the temperature, we expect to see a rapid formation of bubbles, a bit like a really fizzy lemonade. However, if we introduce a catalyst, something that lowers the activation energy, for example cobalt-2 chloride, it's got a pinkish tinge to it. We expect the formation of CO2 to be much more vigorous. Over time, the pinkish hue starts to fade to a chicken juice orange, then eventually green. The cobalt-2 chloride seems to participate in the reaction, and an increase in reaction rate would be evident from a greater formation of bubbles. However, over time, the original pinkish hue would return once the reaction is completed, meaning the cobalt-2 chloride is the same at the end as it was in the beginning, exactly how a catalyst should be. It increases the reaction rate without being consumed by the reaction itself. So how does it do this? Well, simple. By changing the pathway of a reaction so that the bonds can be broken and reformed more easily, which is ultimately changing the activation energy.